Good morning, everybody. It's great to see you in person, and those that are here online, welcome, welcome. Thank you for joining us. We are recording today's session, just FYI. I'm Kim Seno. I'm the Bureau Chief at the New Jersey Department of Environmental Protection, Bureau of Environmental Analysis, Restoration, and Standards. With me today is our Division Director for Water Monitoring Standards and Pesticide Control, Peretti, and we have program staff with us today as well. Yazo Sivaganish, Helen Pang, Crystal Carrillo, Ryan Hughes. Online, we have Thomas Brinken, and I also see Tracy Fay from our director's office is here as well. Our sincerest appreciation to the Barnegat Bay Partnership, Dr. Stan Hales, Andrew McGowan, Bailey Sanders, and of course, Karen Walter for all your assistance in putting this stakeholder meeting together, along with the Ocean County College for hosting these public information sessions. We're incredibly appreciative of the support and this partnership. The purpose of today's stakeholder meeting is to review the science that led to the selection of the nitrogen water quality standard and modeled load reductions in the Barnegat Bay, which is needed to attain a healthy ecology in the bay itself. We presented an overview back on November 29th on the multi-year monitoring effort that served as the basis for the technical work, as well as a summary of the water quality studies and the modeling work that was done. Well, today we're going to take a deeper dive into some of that information and the science that serves as the basis for the work that's been done here in the Bay in these past 12 years. You will hear from Helen Pang, who will discuss the researchers' findings and how it informed the target nitrogen standard. She'll be followed by Dr. Hales, who will discuss the role of the model evaluation group. This was a panel of experts in their fields that provided a critical review of the modeling work that was completed. And as a result of their review, the Department of Environmental Protection then advised the United States Geological Survey on refinements to the modeling work that they performed under contract to the department. So you will hear about that in their presentation. So they are our last presenters, and they'll walk through the models that were developed to address the water quality issues in the Bay. The results of all of these efforts is the site-specific nitrogen target, which is folded into a pollution budget for the Bay. And this is what we call a total maximum daily load, or TMDL. We presented on this at the last meeting. And the TMDL, through the modeling effort, predicts non-point source loading reductions. And as we discussed at the last meeting, it predicts an 80% reduction for the northern portion of the Bay and a 20% reduction for the southern portion of the Bay as necessary in order to attain a healthy ecology. Improvements to water quality in the Bay happen, of course, at the local level, which is why we're here today to share this information and to receive your feedback. So we will during the presentations, pause so often to take comments from the audience. We have folks monitoring the chat online, so we will read your comments out loud, and to the best of our ability, we will answer them, of course, but we'll incorporate your feedback into the writing of the total maximum daily load document, which will be the outcome of these efforts. So today is our second session. Like I said, we're doing a deeper dive into the science, and our first session was an overview. We did record that. The postings are online, and we're happy to share that information with you as well. And we do plan on having in the future, in the spring, a third session on implementation of the TMDL. But for now, let's delve into the science, and our first speaker in that is Helen Pang.
Okay, good morning, everyone. Very happy to back here. So I gave an overview on what we did back in November, but today I'm going to talk about the research project which helped us to develop the site-specific total nitrogen criteria. But before I start with my presentation, you will notice that the format of the slides varies a little bit. The reason is, I'm an engineer. I did not involve in those research projects. I'm a data user of their funding, so I want to respect their work. So I took the presentation from, they gave require. So I don't want to interpret too much, but I try to, talk about the same information they share with the public before. Got it. Thank you. All right. So all the Barnegat Bay work we start as part of the Barnegat Bay initiative. Just want to remind everyone there was 10 action plan under the Barnegat Bay initiative. And then plan 7 was to adopt more rigorous water quality standard by monitoring and modeling. Plan 9 is to produce more comprehensive research. So under Plan 9, there are total 10 research projects as summarized in this table. As you can see from the last column there, for each project, they do have a purpose to characterize the baseline and then fill the knowledge gap. And then for some of the project, they will provide the information in order to make a comparison before and after the power plant closure. Some of the research project, they also provide the information to feed and construct the models, both water quality model and the hydrodynamic model. But the first column, the third column is the biocriteria project. There are 4 of them. So those 4 projects with the purpose for us to have a good understanding of the extent and then the level of course of the ecological impairment. And then we would like to see if there any water quality associated with the impairment of the ecological community, various aspects in the ecological community. So there are 4 research projects. I'm going to talk about each of them briefly, so you will have a sense of the extent and also you will have a sense of the scope and then in the intensity of the effort. So it's just want to give you a feeling it was a lot of work, even though at the end, we only come up 1 criteria. So the first one is the sediment diatom study. It was conducted by the professor and then scholar from Drexel University. Diatom photosynthetic protests found nearly in every freshwater or marine water habitat, and they contribute roughly about 20% primary production and up to 75% algal production in the coastal zone. Assemblage of the diatom are proved to indicate the stressor, such as the nutrient or the climate change. Because their silica shell preserve well in the sediment deposit, diatom are also widely used in assessing long-term environmental changes and then the impact of anthropogenic activity on the aquatic system and also their watershed. The scope of the goal for this diatom study is to study the relationship between diatom species composition and the environmental variables, and also to develop diatom-based model for inferring selected environmental characteristic. Also with the goal to reconstruct environmental history of New Jersey coastal wetland using diatom from sediment cores. So this is the sample we collect here is the sediment sample. We collect a total 110 samples from 100 stations, which cover a wide range of the natural and the anthropogenic condition found in Barnegat Bay and then the Great Bay region. The different sample collection methods were used based on the location and then the nature of the sediment. Both the sediment chemistry and the water quality data were analyzed together with the diatom sample. It's the LLM, the lighting microscope, and then the SEM, the scanning electron microscope method were used to analyze the diatom. And then the multivariate statistical analysis were conducted among the samples being collected, considering the diatom species and then 29 environmental variables. Based on that analysis, the conclusion they draw from the diatom study were summarized here. Diatom assemblage in Barnegat Bay and Great Bay responds to many environmental variables. Salinity is the dominant parameter, but the nitrogen content in the sediment is also one of the factors associated with the assemblage of the diatom. Several diatom species may be used as an indicator of high or low nitrogen concentration. Diatom assemblage in New Jersey marsh evolved toward higher abundance of species, which is an indicator of a high total nitrogen concentration. The rate in change has been accelerating over the last 150 years. So we were hoping that the reference diatom assemblage that inhabited the marsh prior to 1800 can be characterized, and that information can be used as an important biological ending point supporting the development of the estuary nutrient criteria. But by the end of this project, we were not able to come up a nutrient target level which will support based on the diatom species. So that was even though we have a lot of good findings from this study, but we were not able to make that connection between the diatom and then the total nitrogen or total phosphorus concentration in the water column. The second research project is the baseline characterization of phytoplankton and harmful algae bloom. Dr. Ling Ren and then Dr. Donna Charles from Drexel University were the principal investigator on this project. The phytoplankton is as point out here, phyto means plant, and then plankton means drifter. So the phytoplankton is the microscope organism. They are found in the watery environment, both salty and fresh. So phytoplankton, it just behave in the same way as the plant. They will use the light to produce the energy through the photosynthesis. But they differ. The different part is they don't have the root, they don't have the leaf. So they just drift with the water current. Because phytoplankton is the primary producer, so they are the fundamental part in the food web. So the excessive growth of phytoplankton and the occurrence of harmful algae bloom are good indicator of the water quality. So you can see on this map, that's the food web. The phytoplankton is on the upper left corner, and then the next one is the zooplankton. So you just see the relationship because I'm going to talk about the zooplankton project next. The objective of phytoplankton project was to document phytoplankton species composition and succession, and also document the occurrence of the HABs. Also to characterize their temporal and the spatial change. And then ideally, we want to understand the relationship between the change of the species composition and the environmental variable. We also want to develop a season salinity specific phytoplankton IBI, index of biotic integrity, specifically for Barnegat Bay. There were 3 years sampling effort. So the year 1, that was before Hurricane Sandy, we took the sample from 9 stations. They all show on this map. And then in the following year, the sampling location was reduced to 6 of them, as indicated by the station ID with the box. The sampling frequency was monthly during the non-grow season and then bi-weekly during the growing season. The phytoplankton sample will collect together with the water quality sample. So remember, we have the water quality sampling effort. So when people went out for the water quality sample, they took together the phytoplankton sample. And then there are a total 282 samples were analyzed for species composition, cell density, biovolume, and the carbon biomasses for major group. And they also did a lot of analysis, a lot of statistical analysis. So I'm not going to elaborate here, but here I just gave you the summary of their findings. The interannual change in the phytoplankton community vary among sites. Species composition, your northern Barnegat Bay were more affected by Hurricane Sandy. Remember the first year sample that was before Hurricane Sandy. So we were able to see the big impact due to Hurricane Sandy on the phytoplankton composition. We also see the seasonal and the spatial change of phytoplankton. It will primarily controlled by temperature and salinity, but it's also significantly related to total nitrogen, total phosphorus, dissolved silica, the ratio between total nitrogen, total phosphorus, dissolved oxygen, and also the ratio between total organic carbon and dissolved organic carbon. Following the same method as Chesapeake Bay used, the phytoplankton IBI were developed for Barnegat Bay. And then that index was able to successfully classify 57 to 81% of the sample in the calibration data set. And then the PIBI score showed good separation between impaired and the least impaired for most season salinity zone. But as I point out, we are the data user. So when we talk with the researcher on the phytoplankton, we are trying to see we can use their result to come up a total nitrogen number in order to support the unimpaired or the least impaired phytoplankton community or not. They were not able to give us a number which they feel comfortable. So therefore, we cannot come up a number based on the phytoplankton study. The third one is the zooplankton research that was done by the professor and scientist from Monmouth University and then NOAA Fishery. The goal for this project was to characterize zooplankton distribution and abundance spatially and also temporally. We want to correlate the zooplankton community with the water quality data. Also, they want to quantify gelatinous microzooplankton, normally we call jellyfish. They took the sample from 5 stations. That's BB02, BB05A, and then BB07A, BB10, and BB12. So 2 of the stations in the northern part of Bay, 3 stations in the southern part of Bay. It was from 3 years, and then a total 54 sampling event. At the station BB05A, 4 24-hour intensive sampling events were conducted. And then we collect more than 1,000 plankton samples. Based on the data, Barnegat Bay zooplankton community were characterized. So there are pronounced spatial, seasonal, and the interannual variability. Temperature was the most important anabatic variable, and nitrogen is the most important nutrient, and also depending on the location, phosphorus alkalinity play a more noticeable role. Community dominate by estuary species in summer and fall, while in winter and the spring is the coastal species dominate. When we compare the northern station with the southern station, we notice that nitrogen, chlorophyll A concentration are higher in the northern station. Therefore, they have the species is estuary species dominate, and then they have a lower diversity. While in the southern part of Bay, they have a high concentration on the alkalinity, and then phosphorus is the coastal species dominate there, and then the diversity were higher there. Again, we were not able to, based on the zooplankton work, to get a number of the total nitrogen or total phosphorus concentration in the water column, which will support healthy zooplankton community. So the last research project is the benthic macroinvertebrate project. We also, as call here, is a bottom-dwelling animal community. Dr. Barry Tagon and his team from Rutgers conduct this work for 4 years. So the bottom-dwelling animal is a good indicator of the habitat quality because most species are relative sedentary and are relative long-lived. Species differ in tolerance to stress. So the type of species and how abundant they are can be used as an index of habitat quality. This diagram show you a commonly observed response is the species differ in their sensitivity or tolerance to stress. As you see, the x-axis is the stress level. So from the left to right is from low to high stress level. The y is the abundancy of the species. So from left, you see when the stressor level is low, the sensitive species are dominant. When the stress level increase, the tolerant species become dominating. And then when the stressor level extremely high, it will be optimistic species dominate in the system. So we had, under the Plan 9, 3 years benthic macroinvertebrate study were conducted, but since we find the finding was very promising, we actually found 1 more year. So that's a total 4 years benthic macroinvertebrate study. Each year, we took the sample from 100 locations throughout the bay. So it's everywhere in the bay. It's represents spatially. A total 184 species were identified, and then for each species, they were assigned to one of 5 ecological groups. I have a slide following to explain the ecological group. And then we also collect the water quality data that's in the same area as the benthic macroinvertebrate sample were collected. So roughly they're within the 2 kilometer radius. Stepwise linear regression were conducted on both water quality and then the abundance of the most sensitive species. So that's the portion of the most sensitive species. Why I emphasize is the most sensitive species. We have 5 ecological groups. right? We start with the blue one. So that's the sensitive species. So from all the sample we collect, that's about 19%. So they only present under unpolluted condition. And then if we go with the clockwise, the next group will be indifferent. That's 16% of it. So they always present slightly variation with time. The next one, that's 50%. So that's a big part of the sample we collect, is the tolerant species. So they may occur in normal condition, but population stimulated by organic enrichment. And then we move to the next one is the optimistic, that's 8%. They a very short life cycle, proliferate in enriched condition. The last one with the right one, that's the extreme optimistic. And then they only profit in highly enriched condition. So we using the portion of the sensitive species to correlate the water quality variables. And then we did that stepwise linear regression. Via a round of analysis, at the end, we able to find that the total nitrogen concentration over the summertime explain 84% variability of the sensitive species. So we are very excited to come up to find this linear correlation as shown here. The x-axis is the average total nitrogen concentration in the water column over the summertime. The y-axis is the portion of the sensitive species. As you can see, when the concentration increase, the portion of sensitive species decrease. Remember, they only happen within the unpolluted condition. So when the concentration increase, it's not good for them to survive. That's why the concentration decrease. And then based on all those 4 years data, we were able to validate the relationship between those two parameters. So the equation highlighted in blue here, that's the final relationship we use. So it's the proportion of sensitive species relate with the total nitrogen concentration. With that, it's very promising because this is a set-specific relationship we found in Barnegat Bay. If we want to maintain a good portion of sensitive species, we definitely want to control the total nitrogen. So we made a professional judgment and then say, if we want to have a 25% total nitrogen, 25% sensitive species, what will be the total nitrogen concentration in the water column? It turned out to be 450 microgram per liter. So that's the summer average in the water column. So this is the number we think we can use as the set-specific criteria. But normally, when we come up a set-specific criteria, we have to evaluate the system will be able to achieve that level or not. We run a natural condition simulation, so we are very fortunate to have the model. So the model can help us to predict what the concentration would be under the natural condition. So when we take out all the anthropogenic impact, only leave the natural condition there, how the bay will respond. So Vince will talk more about that in his presentation later, but I just want to demonstrate the concentration under the natural condition here. So if you to the yellow color, that's 400 to 449 microgram per liter on this map. So they're all below that. Only a tiny grade, that's the model grade in the Titicaca estuary. But when we evaluate the compliance of that target concentration, we always base on the assessment unit. So there are total 9 assessment units. That means there are multiple model modeling grades in one assessment unit. So even though you see that tiny grade there, but when we average with the surrounding grade, the concentration under the natural condition way below than 450 microgram per liter. So with that, by checking that, we are very confident to say for the entire bay, we only using this universal number 450 microgram per liter as a total nitrogen target. And then people also wondering, how about other estuary program? How our number compared to other estuary program? So we did the literature search. There are various reports, but we are very lucky to actually find this table from the work done by Tetra Tech for EPA on Long Island Sound. They actually did a similar work as we did, but they summarized the information in a very organized way. So I just copied their table. This is the top part of their table. As the title of the table indicate, is a summary of literature review based target concentration for total nitrogen. And then if you check the location, is the Massachusetts estuary or in-bay. That's from various citation. They gave the individual numbers, but if you see the bottom part, that's the summary for total nitrogen target concentration for seagrass protection and restoration. The median value will be 390 microgram per liter. The minimum was 300 microgram per liter. The maximum was 490 microgram per liter. And then the second part of this table is on this slide. So summary for total nitrogen target concentration for other aquatic life protection and the restoration. As you can see, the median value was 410, the minimum again 300, and then the maximum is higher, is 600. When we just focus on the non-seagrass protection and restoration for those total nitrogen target, the medium a little bit higher, 460, the minimum stay 300, and then the maximum also same as the one above, 600. So as you can see, the 450 microgram per liter we pick up here for Barnegat Bay is in the range of all the number used by other estuary program. So that add another layer of confidence for us to use this number. As I point out, I'm a data user of all this research project. So I try to interpret based on my understanding. But of course, I only cover the surface information of the information I think, related to today's topic. But if you're really interested about the detail of those research projects, you can check under the department's Barnegat Bay Plan 9 research report. I have the link here. And also, we have a special issue that's a Journal of Coastal Research for a comprehensive assessment of Barnegat Bay Little Egg Harbor Inlet, New Jersey. So we do have some hard copy here. So if you're interested, you can also get detailed information from that issue. That's all I have. So I don't know if you have any question. Thank you.
I'd like to compliment you on getting a lot of technical information, and I know it all, but I knew a lot of it was applied implementation. I did have a couple of questions though. You used the term on the final point and it said index audit integrity. What does that mean?
It's so as I pointed out, I should say they use the similar approach as used by Chesapeake Bay. So they are calculating that PIBI score will allow them to see this is impaired or less impaired phytoplankton community. So that was the goal for that index.
An index of quality of the life.
Yes, actually, they start with the 34 parameters, but they actually reduce to 9 phytoplankton associated parameter and then 3 chemical parameters. That's to come up with the PIBI score.
Then on the diet talked about the going to something in history that happened in the past. Did they do any comparisons between the north part of the bay and the southern part of the bay? Did they find any significant difference in terms of diet?
Good question. Let me check my, go back to that. Sorry. I do not remember they talk about from top of my head, but I'm sure in the report, probably they talk about, I think the major difference they notice is because the northern part of Bay is under the sandy influence. So definitely they see the difference in the composition.
And are the slides available from?
We will make available. Yeah. Yep.
Okay.
Yeah.
Really quick, if you have any questions, Ryan's going to run the microphone over to you so that the people online can hear the questions. Thank you.
Yeah, I don't know if this has anything to do with this research, but I'm just wondering if the bay is getting saltier as the ocean is rising slightly at this point, and would that make a difference to the biological the research about the nitrogen relative to the biological population?
As we summarize here, salinity is definitely an important parameter to determine the composition of various aspects of the biological community. I'm sure the salinity, the increased salinity will impact, probably not in a short term, but the long term, we will see the change. But just additional study will be needed in order to see that difference.
Okay, thank you.
There actually may be data to answer that question, but I don't think people have looked at it carefully.
Okay, we had one question from the chat, and it was regarding the diatom study. Catherine asks, what was the connection that the research project couldn't come up with?
Could you repeat that question? Sorry.
Yes. So regarding the diatom study, what connection did the research project not come up with?
I guess the question is why we cannot draw a connection between the diatom community with a water quality target. Is that?
Yes.
Again, we are the data user, right? So when I talk to the researcher of the diatom, I was asking, based on your observation, will you be able to recommend a number for the total nitrogen concentration? They only tell me they see the impact, but they cannot draw a clear line, say, hey, if the concentration is below this, the diatom community will be healthier. So that's why we only take their input and then not to make any conclusion.
Thank you. Charles just put in the chat, what was the rationale for having a single standard for the entire bay at 450 rather than having differing standards for sub-watersheds based on their nitrogen loads?
Very good question. As I point out, this 450 was determined based on the macroinvertebrate sample. And then as I point out, that was a total 100 stations throughout the bay. And then those locations was randomly selected to have a good representation of the bay, the situation within the bay. And then the correlation we developed, that's based on all the sample we collected. So it's not just like from the sample in the northern part of bay or the central part of bay. Every single sample collected within the bay, that relationship valid. Therefore, we think this 450 number is applicable to the entire bay, not just part of it.
Thank you. No more questions.
Okay. All right. Thank you.
Thank you, Andrew. I'd like to talk a little bit about the model evaluation group that was done several years ago and reviewing this. And I want to acknowledge Dr. Jim Vasilides, now with NOAA, who basically did the bulk of the lift with coordinating the efforts of the group. And Jim's sitting in a dentist's office right now. I wish him well, but otherwise he would be here. So just as Helen did with her presentation, I'd like to reach out and acknowledge this started with former Governor Christie's 10-point plan in 2010. These were the 10 elements of that. A lot of things were set in motion since then. And I think it's important to recognize that there's been follow through on all of these things. And I think everyone should commend DEP for the follow through and keeping this all alive. I too am going to focus on the same two elements that Helen did, the rigorous water quality standard and the comprehensive research. I'm going to go through some of these things pretty quickly, but I want everybody to recognize the comprehensive nature of the work and just the volume, the amount of work that was done to develop this. It seems pretty simple to say, let's just go develop a TMDL, but a lot of information and a lot of different kinds of things go into that assessment. It's important to recognize that 8 partner organizations of DEP and the Barnegat Bay Partnership started work to support the state's collaborative monitoring network. Lots of stations, lots of different kinds of activities. This was a major commitment by a bunch of groups, and the state did a good job in supporting it and maintaining. At the same time, under separate funding and with USGS funding and some other funding streams, USGS also started its own comprehensive research programs that supported some of these things, basically bottom characterization. They started some modeling activities, and this was also important to the development of this. And as Helen recognized, a lot of that work was published in one volume. And it's important to keep in mind that all of that work continued despite a significant challenge dropped in everyone's lap right in the middle of it that severely impacted a lot of that ongoing work. So we know how much Sandy impacted people in the coast of New Jersey. It also impacted the science of New Jersey, but nonetheless, we persevered and worked through it. And one aside, also during this time and start of 2018, Oyster Creek Nuclear Generating Station was closed, and it had an impact too. I want to talk a little bit about the MEG development because the MEG you couldn't even think about assessing the development of a model or what it was doing or how it was working without all of those early steps. And at the presentation of all of that science at a meeting here, we had a very brief conversation with the department about taking a look at the modeling. We submitted a proposal to the state in November of 17 and December of 17. I said they got back to us and said that it looked good. We'd work something out. We received a contract in 2019, and there you see the scope of work for that model evaluation group. want to talk about these parts in some detail. The first part of this was to develop the terms of reference. This basically is just an agreement on how that evaluation was going to go. This was done jointly, collaboratively between DEP, USGS, and the BBP team, which was Jim and me. In spring of 2019, we set up a review team. And, there's peer review and review of scientific work has always been very much a core principle. There was various opinions expressed that, it would be good to get some outside review of that. So we set up a process basically to engage and work with all of the partners within the BBP to set up that MEG review team. And so what we did is we opened up a solicitation for people to submit reviewers to be members of the MEG team. From all of our partners, we received a list of 16 different names. Jim did a great job in sort of compiling background information on all of those people, and many of them are well known to lots of people in science who do this kind of work. Some weren't, but we asked all of the members of the partnership, the STAC and advisory committee, I believe, to weigh in on the qualifications to these people and make recommendations. And the point was to find people that had not been working with DEP or USGS closely over this. So essentially there was no conflict of interest. So the STAC members recommended their top choices. And 4 of those people basically agreed, accepted contracts, and became team members. Now, when the report comes out, I
Still not sure.
sorry. The report's not yet released, so I have the comfortable position of talking about the MEG without talking about the MEG. So I hope everyone appreciates that. The 4 team members had over 100 years of experience in water quality modeling work. It included former federal employees, members of academic institutions, and people also who worked in private industry. It includes some of the most well-recognized modelers in the history of water quality and hydrodynamic modeling in the U.S. So we had a very good, experienced team, and we got back to work. Basically, the MEG terms of reference, the scope of work, these are the general tasks. The first part was to review the ROMS model. This was the hydrodynamic model that USGS had developed and assess that. The second was to review the water quality model to ensure that a good job had been done with that component. The third part was to look at the coupling between the 2 models. It's not a trivial task. You want to know how the water moves around the bay. There are lots of different drivers of the circulation around the bay. And there are a lot of biological processes which affect the quality of the water in all the different parts of the bay. So those are 3 non-trivial tasks right there. And then lastly, the question was to determine if the model outputs were adequate to meet the department's need for developing a decision-making tool. So what do? We developed a list of questions. Those 4 general tasks turned into about a dozen specific questions. And then we asked the MEG team what they needed to do that assessment. And so they compiled a list of various data streams, metadata, reports, calibration, validation activities, everything that they felt was necessary. And keep in mind, these were people who do this kind of work for a living, so it was a long list. Now, in our original budget and schedule, that was a 3-month task that turned into a 9-month task. And there was a lot of exchange back and forth about that. It was a lot of work. Part of it is an acknowledgement of all the work that had been done over the preceding few years to generate a lot of science. So a lot of things had to be pulled together. There were several additional requests for information after the MEG team got started doing the review. I said, well, we thought we had everything, but we didn't. We need this too. And so this also was time taking. So we got everything. We held a 3-day meeting here at Ocean County College. And we had that meeting in late winter 2020. This 3-day meeting, this involved USGS staff, department staff, the MEG team, and us. And this is essentially what we did. There was a lengthy presentation on the hydrodynamic model the morning of the first day, and then there was a lengthy follow-up discussion that morning. Then we had a lengthy presentation regarding the water quality model, and again, that was followed up with discussion with the MEG team. And then the next day, we started on the third task, that linkage model, and then in the afternoon, the model applications. And then on day 3, the MEG team met just with Jim and me, not USGS and DEP, to discuss their recommendations, conclusions, findings, etc., and next steps. And so you're all curious, well, what were the findings? The first thing the MEG said was, you all know a lot about Barnegat Bay. You've collected a lot of information. We want to applaud you just for pulling all of that information together. That was a tremendous undertaking in and of itself. They were very complimentary of the hydrodynamic model, and I'm not going to go into any more details on that. Those will be released with the MEG report, but when you see it, you'll know, you'll recognize that as the conclusion. They're also very complimentary of the linkage between this model, and this was probably one of the more challenging tasks, but they said it was really well done. With regard to the water quality model, they said it was probably adequate, but they had a lot of questions and some concerns, and they made a number of recommendations I won't go into, but essentially this was creating some work for people to go back and take a look at. And then next, as I mentioned, Sandy had occurred during the course of all of the research that was being done. Sandy basically ended the data used in the model at 7 months. And this was recognized as a concern, a significant concern, because the model had not actually been used to look at the movements of water and changes in water quality throughout the course of a year. And that's pretty much standard for that kind of business. And that was problematic, and there were some suggestions made regarding that. And then lastly, they recognized that the model, the water quality, the integrated model was usable with everything except turbidity. All right, so turbidity was a challenge that was not addressed. All right, so where do we stand with the MEG? The MEG is not an end-all in itself, and the MEG report is not a reflection of the status of the work of the modeling at this point in time. So basically, the MEG was an evaluation of what was going on 4 years ago in 2019, 2020. So it provided a useful review and a progress report there, and it made a number of recommendations that the department and USGS have had 4 years to act on. The MEG provided some recommendations and directions for the department to move forward with. They recommend, or the report acknowledged, that there's been tremendous, again, improvement in our understanding of the Bay. And lastly, the report makes clear that a TMDL is not going to solve all of the problems facing Barnegat Bay. So I stepped back from looking at the MEG and have tried to put that in perspective in sort of a bigger fashion. In 2008, Walter Boynton spoke at a meeting at Georgian Court College. And one of the things he pointed out was sort of his assessment. Walter was head of Chesapeake Bay Science Program for a long time. He's, one of the worldwide leaders in studying and thinking about eutrophication. And here you see the nitrogen and phosphorus loads along the x-axis for something like 30 or 40 estuarine systems in the U.S. And he said, I don't get it. The nitrogen and the phosphorus load for Barnegat Bay are really not that high, but based on all the information in front of him at the time, it looked like the bay was extremely sensitive to that load. And so he said, the first thing to do is you need to figure out if that really is the load. And then we need to think about this problem more broadly. At the time, there was only a single estimate of the turnover time in the water of the bay. It was done by a graduate student, and it was something around 70 to 115 days. So it was a relatively long residence time of water in the bay. You could almost think at the time that the bay was like a bathtub. But with all of the science that's been gathered since then, that view has somewhat changed. So the first thing is we know a lot more, that we have some confirmation of some things, but we don't really have a single bay that's a bathtub. We have different bays with different parts and things like that. So there are some different kinds of challenges. The other thing is, if we adopt a TMDL right now, and we haven't heard more detail, we need more detail from the state and USGS regarding that, support for that, but I think we're on the right track, and we're headed very much in the right direction. But if we turn off all the nitrogen and phosphorus to the bay tomorrow, work in other estuaries would suggest that we might not see a response to the bay for 5 to 10 years or so, and that other things may happen on down the road. There could be another system, another storm, other things that could happen that could indicate. And this is the best example I could find where people have pulled together this kind of information for a long time. And I'm sure there's a slide since then, but this is something that Holly Greening put together for Tampa Bay back in 2010. And so you can see, after taking a lot of steps to address nutrient loading to Barnegat Bay, conditions got really good, but there was a lag. So we have to be patient as we move forward with implementing this TMDL, and it's going to take everyone's support for it. This was with a lot of groups spending a lot of time and money to address it. And this last slide was from a different Walter Boynton presentation at a different meeting, but he pointed out that oysters and marshes tend to reinforce all the different things that happen within a bay that's got nitrogen and phosphorus loading. And he said, basically, you need to keep in mind, and so that you need to support wetland restoration and you need to support SAV restoration. And I thought important just to, and the other thing he added, I think, was shellfish. But I just wanted to make the point that the state's already started spending money on wetland, shellfish, and SAV restoration. And so these are things that, in addition to just turning off the nutrient loading, there are other steps that we need to take. So if I look at these other pieces of work and combine it with where we stand with regard to the development of the TMDL, I think we're very, very much headed in the right direction. But I think it's important for everyone to keep in mind that just reducing nitrogen and phosphorus alone is not going to do it. We need to take some other steps as well. So, any questions?
We had one question in the chat. What does the modeling show? Whoa, I'm so sorry. Oh, sorry, I'm going to start with Catherine's question. What was the MEG findings before Sandy and how did this affect after Sandy?
Well, there were no MEG findings before Sandy. So the MEG didn't start its work until 7 years after Sandy. So there's no pre and post comparison to my understanding.
Thank you. And then Charles asked, what does the modeling show when you input N values that are higher and lower than the 450 target?
I don't think I can answer that question. I'll leave it for our colleagues at DEP and USGS. Maybe can consider that in their presentations.
Thank you.
All right. Thank you.
One quick question, you know, I'm not a scientist now, but your statement that, reducing nitrogen phosphorus alone is not going to be it. But and the great work that it was doing for weather, but for SAB shelf, we really need to start to reduce nitrogen phosphorus.
Oh, I'm not saying that we don't reduce nitrogen and phosphorus. We very much need the TMDL to do that.
Wouldn't that need the lead to
It certainly helps. You know, one of the things that wasn't recognized in 2008 was the impact, the importance of turbidity in the bay. And so turbidity is a big issue. And unfortunately, you know, there might be some way to model it, but you'd probably best ask that of others. But as you know, the bay is shallow, and every time there's a wind event, depending upon its magnitude and duration, the waters get stirred up considerably. And that, separate from nitrogen and phosphorus impacts, can impact SAV. Sure.
Okay, folks, we're going to get started again with the second half. With us today, we have the United States Geological Survey. They were the partner with the department in this effort, and you will hear the details of the modeling that was done in Barnegat Bay. So I'd like to invite USGS up and we'll get started. Thank you.
All right, everybody. Thank you for having me. I'm Neil Ganju from the USGS in Woods Hole. And my colleague Zafer definitely did the majority of this work. I am just the project leader from 10 years ago. I'm going to try to remember everything we did. It's been some time, but some of the best work we've ever done was done in Barnegat Bay. And I also want to point out that the work that the state supported through this Barnegat Bay project did not stop there. It actually ended up being the seed for national work that we've done, including remote sensing of wetlands across the country. So a lot of good work came out of this Barnegat Bay project that's still going on in our office. So I'm going to talk specifically about the hydrodynamics, but I'm going to show you the overall objectives of the modeling project that the USGS undertook. So as you saw from both Kim's introduction as well as Helen, our goal was to build a suite of models that could be used to inform water quality issues in the bay. So specifically, the first thing, which actually isn't even mentioned here, was building a new terrain model for the bay. So actually measuring the bathymetry using boats as well as airborne LiDAR to actually update the maps of the bay, which were previously from 1930 and onwards. So it's kind of a hodgepodge of data that we had to update in order to even build the models in the first place. After building those models that we're going to talk about in detail, then calibrating them and applying them into different scenarios of management in order to inform water quality. So I'm the hydrodynamic part of this, and one of the key things in hydrodynamics is the grid. So actually building a grid with the proper resolution. So you're taking a map of the bay and you're chopping it up into little cells like you would in a puzzle. And getting those cells the right size is the key to getting the movement of water correct. So we did several iterations of this. This was the final iteration. So this is what the grid looks like. Resolutions variable depending on where you are in the bay. So at the inlets, we have the finest resolution, so the smallest cells, about 40 meters, and then in the wider expanses of the bay and offshore, about 200 meters. All these other models that are mentioned here, the ADCIRC model, the North American model, Rutgers model, these are all state-of-the-art gold standard models that are used to actually force is the word we use to actually put the boundary conditions onto these models. So for example, that North American mesoscale model, that one's actually taking solar radiation from the sun, wind data, rain, humidity, and feeding it to this hydrodynamic model. And that's the model that folks use all around the world to force data of that type. The subtidal model that's there, that's to give you what's going on in the ocean. And that model comes from Rutgers, a model they call Espresso. And actually, Rutgers built the ROMS model code several decades ago. The R in ROMS actually stands for Rutgers originally. It stands for regional now. So we built that model using all of those inputs. It's documented in a number of publications and still in use by several parties across the country, both here in Jersey as well as international researchers who've used Barnegat Bay as a case study for things like salt marshes and hydrodynamics. And again, as Stan pointed out, we ran this period starting in March of 2012 and then had to stop because of Hurricane Sandy and its disruption. We actually modeled Hurricane Sandy separately in another paper. If anybody's interested, we can talk about that another time. This is just an example of why the grid matters so much. So this is a zoom in of Barnegat Inlet. And on the left was the very first grid that I built. And of course, Zafir did it much better. So he came and built the grid on the right. And what you can see is specifically around the inlet, I'm going to try to point properly. If you can see right in the inlet, the resolution gets much higher in the new grid. And you want that resolution to be very fine at areas like that because the water is moving faster. When the water moves faster, you get more errors if you have the wrong grid size and the wrong time step. So this is just an example of one improvement that was made before even testing the model. The next improvement we had to make was actually implementing changes that had been done both because of just natural change in bathymetry, but also changing of the inlets through hardening of the shore and stabilization of Barnegat Inlet. So what you're seeing here are three cases. The top case on the right there is the 1930s bathymetry, and then updating of the inlet channel as it was dredged and constructed and trained. And then the third case with the actual modern bathymetry put into that. And what I'm trying to show here is that as you change those cases, you start matching the tides much better. And so that big set of bars you see here is that 12-hour tide that we get in Barnegat Bay and the amplitude of it. And you can see the amplitude gets better to match the data in red as we update the bathymetry in the inlet. So these were the kinds of tests that we had to do before even assessing whether or not the model was doing well. So then once we had a calibrated model where we had the right inlet geometries, we have the right bathymetries, we have the right forcing, we do what we call a skill assessment. So you run through all the available data, in this case, water levels and flows through the different inlets, and you assess it. And what we use is this thing called the Breyer Skill Score, which is the BSS over here. And what you have to understand is a skill of 0 means you're doing only as good as the mean. So let's say you ran a month of simulation, and the temperature in real life is going between, let's say, 15 and 20 Celsius, going around and around and around. A skill of 0 would mean if you had a flat line in the model of 17.5 degrees. So you're capturing no variability, but you're getting the average conditions right. That's a skill of 0, and that would be considered poor. Actually, I think it might be fair. In the literature, they have ranges, verbal ranges of these data. So these aren't just words I made up to tell you things are excellent. Those are actual ranges. So you can see above 0.8, you get excellent, and 0.5 is actually considered good because you're capturing half of the variability that's moving around. So these are considered kind of standard metrics and overall pretty good. Now, when you look at them in detail, these are the data collected by DEP and USGS for water levels at 3 spots in the bay. Basically, in red is the model, and blue is the data. One of the big things I wanted to point out is, we capture the tidal fluctuations really well everywhere, but you can see periods of mismatch. For example, there's a big offset here where the model thinks the water level on average is a little higher than the data does. Those are things we can't really control for because they're happening on the offshore boundary out in the ocean, and that data is coming from another model, which is all you can use because there are no data out in the middle of the ocean. Nobody's got a water level sensor 10 kilometers offshore. That kind of data just doesn't exist, unfortunately, yet. We're going to get it from satellites eventually, but not yet. So there's some errors that are just coming from these other models that can't be helped. For water flows, so these are the actual volumes of water flowing through every 15 minutes is what we're showing here. And you can see really good agreement. And you need to have this right in order to capture the way water is flowing through the bay. So the general south to north trend of water flow that we, not just us, have seen, but Rutgers had measured that years ago. We confirmed it. Other studies have seen it. That general flow from south to north in the bay is controlled by how these water flows happen within the inlets, as well as that water level difference in tides from south to north. So all these things are just lines of evidence for this general northward flow in the bay, higher residence time in the northern part of the bay on the order of 30 to 40 days. Now, if you think about what Helen was showing in terms of some of the biotic indicators, temperature and salinity were the two most important things. So it's imperative that we actually can model those properly. So this is showing the model results for salinity at the surface and then at the bottom from the different sampling stations. And overall, you can see it's doing a pretty good job. The error is about 1 PSU out of 30. So that's, about a 3% error. And what this is telling you is that the model is capturing what's coming into the boundary. And again, that's held by the bigger model, holding it at 30 to 32 PSU and changing with oceanic conditions. And then the river's coming in with fresh water, which we're getting from the USGS gauges. So those two things come in, the model has to mix them. So the agreement is telling you that the model is mixing things correctly. So the way water is flowing and salt is mixing is being done correctly. And then even more importantly for water quality is temperature. And you can see really good agreement here. And temperature, again, is happening, the changes are happening because of what happens on the oceanic boundary, but also because of the sun and the heating of the water in the shallow parts of the bay. And what we've seen in several studies after this one is the solar radiation and the air temperature control the water temperature within Barnegat Bay more than anything else. So it's imperative to capture that process as well. So once we built this hydrodynamic model, and that's shown here at the bottom, the bigger model is called COAST, but we're just using the ROMS portion of it, which is what moves the water around. Once we built that, we needed a way to pass that information to the water quality model. There is no EPA sort of approved water quality model within ROMS. There's other kinds of biogeochemical models, but not things that capture dissolved oxygen, nitrogen dynamics. So the WASP model was the one that EPA has used. So we had to build a linkage between the hydrodynamic model and the WASP model. So what does that mean? It means we have to pass to WASP how the water is moving. We have to tell it what the temperature is, what the salinity is, and then WASP has to digest that and run its own codes. So to build that linkage, that was a novel thing that Zafir had to do. He did a great job of it. They published a paper showing that linkage. And in general, really the first step is the hydrodynamic model, again, is run at very high resolution so that we can get the water movement correct. WASP cannot run at that same resolution. It doesn't have the computational ability to run at that very high resolution. So we have to kind of aggregate up. We have to lump cells in ROMS that are very high resolution, lump them together, and then pass them to WASP like that. Now, if you're doing the water movement correct, aggregating, lumping things together should be fine. If you think about, a 5-gallon bucket and, 5 1-gallon buckets, you can balance the same mass of water if you're measuring correctly, right? And if you're emptying those 1-gallon buckets correctly into the 5-gallon bucket, you'll get the same mass out. That's all we're doing here. We're making sure what empties out of 5 cells in ROMS gets into 1 cell, for example, in WASP. So we built a couple of test segments. So for example, the Toms River segment you can see in the bottom left was one, and then a couple others. We're taking little subsets of the WASP grid, and we're confirming what we're putting in, what's coming out, and what's getting stored in those cells. It should match. It's a simple mass balance of water. And so we ran a set of tests here. This is the workflow for it. And in the Toms River case, what you're seeing on the left here are the ROMS grid showing salinity, vertical salinity gradients in the model, and then along the channel of the river from ROMS from 2 different times going from ebb into ebb tide here. So that it's getting fresher up top. So this is what ROMS is doing. We pass that to WASP, and this is WASP recreating that. So this is one check. The second check is confirming that what comes in, what goes out. So we know that what we're putting into the WASP model, into the ROMS model is coming out at the exact same rate. And that's why that line looks so good. All those data points match. And then lastly, we can confirm that the salt in ROMS and WASP are matching, and they match the data that was collected. So we have a perfect match there indicating that we made no errors in passing that information between the two models. And I know that was a lot to cover in 15 minutes, but I'll take any questions and dive in as needed.
I was just curious if the models that you talked about, can they handle extreme events like a storm surge and a blowout tide?
Yeah, it's a great question. One of the beauties of these kinds of deterministic models that are doing the very fundamental laws of motion is that they will capture those extreme events. So, for example, we modeled Hurricane Sandy with good skill, and that's published in a paper. What these models can't do is respond if something structurally has changed in the system and you're not accounting for that. So, for example, if you wanted to capture, the breach at Mantelogan, you have to actually make sure that that gets modeled in and changes the grid, right? Because the bathymetry changed. So we did that in that paper, but that's not something that happens automatically. The modeler has to make sure that those feedbacks are in there for extreme events.
All right, and we had one question in the chat. What approach did you use for averaging the ROM high-res mixing into the coarser WASP grid?
Yeah, great question. So Vince could probably speak more accurately on this, but if I remember correctly, ROMS is providing WASP with the salinity at the boundaries. So on the oceanic and, well, that's not correct. ROMS is actually giving WASP the specific salinity in each aggregated cell, correct? That's correct. Okay. So WASP itself is not doing any of the mixing. ROMS is doing the mixing, and then cells are getting averaged together in ROMS at bigger scales and passed to WASP. So WASP isn't doing any mixing. ROMS is doing it all with the standard hydrodynamic principles of turbulence and mixing. So I hope that answers that.
Thank you.
All right, thank you. And now Vince will cover the rest.
Good morning. My name is Vince DePaul with the New Jersey Water Science Center, USGS. I'm going to talk about the water quality model. So the water quality model that we've used, and we've heard it referenced a few times, is EPA's Water Quality Analysis Simulation Program. And in specific, the Advanced Eutrophication module. This is a multi-dimensional. It could be run in 1, 2, or 3D, multi-species and transient. There are 24 systems and up to 10 algal species that are available, plus sediment diagenesis. For the Barnegat Bay application, we only utilize 16 systems, and we put in 2 composite algal species, a diatom and a non-diatom. And on the right is the table of the model state variables that we actually used. I don't expect you to read them, but that just shows what was in the Barnegat Bay model. So some of the recent enhancements, the original model was done in old version 7.5, and it's no longer supported, no longer even running. So some of the recent updates include an updated light and reaeration routines. We've added phytoplankton toxicity to salinity and fresh water. There have been some updates to the diagenesis model, including initial condition restart capabilities, and also a hybrid method. And then most importantly, this is the current version that's routinely updated and has full support by the EPA. So this slide speaks a little bit to passage of data that Neil was talking about. The left figure shows the ROMS grid discretization, while the right figure shows the WASP grid discretization. Given the computational burden in the water quality model, we had much fewer cells available to us. Thus, the model had to be aggregated and resampled in time in order for it to speak to the water quality model. So the output time step was resampled and grids were aggregated. So the ROMS grid, one unique aspect of the water quality model, the ROMS has a 1-to-1 segment connectivity, which means one cell face to one cell face, time step of 5 seconds. WASP has one-to-many connectivity. That's 1 to 2 or 3 cell faces. And the time step for the water quality model was 60 seconds. Overall, the ROMS to WAS segmentation is about 100-to-1 ratio. And this just shows you a detailed inset of the Barnegat Bay Inlet. The dark blue lines are the WASP model grid cells. The light gray ones are the ROMS cells. As Helen has presented in a previous talk, the WASP model is forced or loaded from various sources, all of which came from Barnegat Bay research work. So the most influential boundaries are those at monitored water at the monitored watersheds, the tributaries, and the ocean inlets. So at these points of entry, we specify species of nitrogen, phosphorus, silica, dissolved oxygen, biological oxygen demand, chlorophyll A, and solids. And these boundaries are set into the model as concentrations, and their time series, and they range from daily to biweekly. At unmonitored some basins, this is pretty much all estimated data. We don't have any actual data that was collected, and it gets all the same inputs except for phytoplankton. Both direct groundwater discharge to the bay and the Morris Estuary interaction were imposed as external loads, and they're not really dynamically introduced into the model. So those are not concentrations. They go in as kilograms per day. In order to determine the benthic sediment fluxes, we actually did link a dynamic submodel. This considers or outputs dissolved inorganic nitrogen, phosphate, sediment oxygen demand, and it relies on the organic content of the model's sediment layers, as well as temperature, light, and the concentration that's in the water column. Light attenuation is addressed dynamically in the model, and the model resolves this attenuation from solids, algal shading, and dissolved organic matter in the water. This requires detailed solar radiation input, and we also have hydraulic and wind driven reaeration, and that's included in the as part of the dissolved oxygen budget. And for that input, we need local air temperature and wind speed are the required inputs. So the model is loaded at all flow boundaries. And again, the most influential are the tributaries and the ocean inlets. They have the broadest impact throughout the bay. These boundaries are derived from observed data, whether it's discrete or continuous, and they are enhanced at selected boundaries using standard USGS regression models. A load estimator was the most widely used one, and I think there was a few that got a WRTDS model. Many of the state variables that actually go into the model are directly measured through DEP partners. Some, however, need to be calculated. We don't measure the organics or the detrital compartments directly. For the unmonitored watersheds, I mentioned that this is all estimated. The first step is it requires flow estimation and downstream water quality. So basically, it's a pretty simple way to do it. We relate an unmonitored watershed to one that does have data based on its landscape type and physical characteristics. And we do a transfer of the discharge and water quality using this hydrologic similarity. And the computed time series loads are loads for these unmonitored sites, and they're entered at the appropriate model segment. One important point to make is that the associated flows are not included in the hydrodynamic model. So loading via direct groundwater contribution is first estimated by performing a pretty detailed water budget analysis of an existing Southern Ocean County groundwater flow model. So we carved those discharge zones into 21 separate estuarine, and wetland zones. Total discharge, and if you look on the map, the total, the blue shading is discharge areas. The green is actually wetlands. However, the wetlands accept an enormous amount of the discharge coming from the watershed. Total discharge is about 97 CFS. That equates to 63 million gallons per day. These discharge values are then paired with representative water quality from the sites that are shown on the map. And then a direct groundwater load is computed. Most of the water, as you can see, is discharged to the central and south. And constituents such as a nitrate are much lower in the south than in the north, where the groundwater end loading rates are generally greater. So what we see for a groundwater load is considerably less than what we've seen in past estimates, given that past studies have just taken one flow number and one water quality number and applied it basin-wide. Here we're taking the actual compartments on the map and looking at the individual introduction of available nutrients with their respective flows. Much like the groundwater loads, salt marshes are also not a dynamic interaction. They're also imposed as a load in the model. The first piece to doing this is estimating the typical daily inundation of the marsh parcels by reclassifying the elevations of a digital elevation model by the water level duration in the nearby bay gauges. So the hotter colors on that map indicate marsh parcels that are underwater for longer periods, and it's in days per year. So the denitrification rates come from another Barnegat Bay researcher, that's David Valinsky, and those are applied to the marsh area by normalizing to the daily inundation period to estimate the load. And then these loads are applied as a constant, but they're applied in the negative as it's a transformation or loss. And the overall estimate is about 50,000 kilograms of nitrogen per year that the marshes pull out from the watershed. And we also imposed a CBOD loading rate at 6 kilograms per day, given the carbon export off the marsh platform. And this was just a value pulled from literature. So once the model's loaded, the next step is begin the calibration period. So at the beginning of the calibration period, or actually a little bit past that, there are multiple screening level sensitivity analyses, and this is really just for the purpose of determining the most influential parameters. It's not a rigorous analysis. We just want to know what's actually driving the model. The calibration period that we're looking at is April to September. Remember, the simulation period started in March, but the model needs some time to spin up, despite the fact that initial conditions were adjusted. The model runtime for the fixed time step, which is 60 seconds, generally takes about 7 hours. And we also had another hydrodynamic file built that runs on an optimized time step. And that's for sort of mass production, mass runs. Any finished run actually would get the 60-second fixed time step. So the model is calibrated by the manual trial and error method, which is still done. And that's done basically by adjusting model rates, kinetics, sometimes estimated boundary concentrations and loads. And the general focus is actually on matching the general spatiotemporal trends and not doing a point-to-point. They are based on graphical and statistical matches. However, we don't rely on the statistical numbers too much. Once the model is calibrated, we evaluate the model sensitivity in a little more rigorous fashion. And we want to quantify the effects of individual components on model solution. And what this will allow us is it provides some information on model uncertainty. So I'm going to show a couple of model data comparison graphs. This slide shows data comparison for water temperature. As Neil mentioned, water temperature is not a WASP state variable. However, because of its importance in pretty much every reaction that's happening in the model, we want to make sure that the model is interpreting the aggregated numbers correctly. So the 4 sites are shown on the map to the left. And as we can see, the discrete temperature and simulated data are actually a very good match. All statistical metrics for these 4 sites would be considered very good or excellent. This is a similar graphic. We're looking at the comparison from the model data and the continuous data. And again, we see a very good match with temperature. This is more model data comparison. We're looking at this figure shows a snapshot of model and observed data along the navigation channel for total nitrogen in the summer of 2012. So the range of these samples are from mid-July to about mid-August. The gray polygon that you see is the WASP simulated daily range. The red dots are the observed data. Ideally, you would want the red dots to fall inside that polygon, but overall, we have a decent match. Actually, it's good. And in some cases, though, we see that we do underpredict nitrogen a little bit, and model-wide, we do underpredict it by about 7%. And this is the more standard time series type graphic. And again, we show a pretty good match. We're not capturing every point, but we do capture the central tendency of the data. So what does this look like? So this slide is showing us the spatial and temporal structure of nitrogen in the bay. Again, these are averaged numbers from July to September, as everyone has shown and talked about. So we see TN is very elevated in the north. The mean concentrations range from 0.59 to 0.65 milligrams per liter. The highest means occur in the Tom's estuary. The highest max in the Petitconk area at greater than 1 milligram per liter. And the map on the right is actually a duration map. It's providing the percentage of time during that summer period that nitrogen would exceed a given threshold. And in this case, we're using 0.45. So nearly 100% of the time, it will exceed that 0.45. In the central and south, concentrations are a bit lower. The highest means occur in Manahawkin Bay, Upper Little Egg Harbor, highest max in the same place. The difference is that those concentrations will be exceeded less than 10% of the period. So that's just the part of the model build. Are there any questions?
Thank you. Yeah, I'm not a scientist. I'm just a Joe on the street, but a quick question. All this information is from 2012, correct?
It's a 2012 simulation, correct?
I live in Orchid River, Lacey Township, and in 2018, they closed Oyster Creek. Do we know the impact of something that was being produced on Barnegat Bay artificially, as opposed to, since its closure, how nature has recovered from that artificial, change in water flow, et cetera?
Well, we haven't run any updated scenarios to speak to that, but some of the hindcasting where we're putting in a run without the Oyster Creek Nuclear Generating Station in it. And the biggest changes, you're going to see changes in velocity and water level right near the mouth of the Oyster Creek, but the biggest change is obviously going to be temperature.
Temperature, yeah.
And we do have a few slides that speak to that.
Yeah, it'd be interesting to see over time how how the bay recovers from that. Thank you.
Okay, so in the chat, I'm not sure if you can answer this question or if somebody else can answer this question, but it asks, could the modeling be used to predict what happens if the Army Corps builds floodgates at the Barnegat Bay Inlet? Or the Barnegat Inlet?
As it's constructed now, no.
No.
That would need another hydrodynamic model built to address that. And then we could build the water quality back on top of that.
Okay, thank you. And another question, the modeling time period seems very limited for a sediment diagenesis model to equilibrate. Did you have to recycle over and over via model runs? Was the sediment diagenesis model employed for model projection scenarios? Wondering, how did you deal with the limited time for the sediment to equilibrate?
Yeah, I mean, that's a great question, and it is a very short time period for that. So the best we could do is run the model sequentially or consecutively 15 to 20 times and let all that settling flux of organic material build up into the mathematical sediment layer. And over time, we see the equilibration of say, particularly organic carbon and other organics in the labile and refractory layers of the model. So that's how it's not the best way to do it. I mean, the best way to do it would be to run a 10-year simulation, but that's what we had and that's what we did.
Thank you. And that's all the questions online.
So we could start on with the scenarios. So the first scenario that we built, and Helen showed this and talked about it a little bit, was the natural conditions scenario, which is setting the model as minimally disturbed. And this is necessary to arrive at the lower constraints on any potential target, and also to identify areas of the bay that may not meet a target under natural conditions. So the assumptions, we used a different hydrodynamics, and this had the Oyster Creek Nuclear Generating Station taken offline, and we used that for all subsequent scenarios. Any developed land within the watershed reverts to a forest signal, and this is these values were assigned based on water quality data that we pulled from what we considered minimally impacted reference watersheds. One limitation is that this does not discriminate between the reducible and non-reducible land uses. For atmospheric deposition, some airshed modeling by the New Jersey DEP informed us to use a marginal decrease of about 13% for the direct groundwater component. That's the SGD. We applied a lower magnitude loading rate at the northern segments and kept the others as is. And the final point is the watershed hydrology and marsh components remained unchanged. This just shows the location of the 3 reference stations. And this is comparable to a landscape type approach, and it utilizes locally derived data. So the criteria for looking at these basins and this data goes back to prior to 2012. That they were located within the Barnegat Bay watershed, that they were greater than 90% undeveloped with at least 70% forested land and minimally disturbed, less than 4% urban and less than 0.5% ag. So what we did, we composited the data from those 3 sites and made one data set. And we developed a time series, and then we actually ran standard quantiles, and we pulled the 75th percentile out for each variable, and we applied that seasonally and by flow condition within the model. So this is a slide that actually shows us a little bit about the difference between Oyster Creek online and offline, and this is just temperature. So the map on the right, on the left, is with Oyster Creek still operating, and we see the right by the mouth of the Oyster Creek, we see a temperature high. The map in the middle is offline. And with the generating station offline, we lose the thermal high at the mouth of the bay, and the water is slightly cooler, hugging the shoreline. But the effect does dissipate within a short distance. So the smaller inset on the right is the differential, which is the maximum in this. Again, this is summertime, and these are this is a larger grid, so it's averaged. We see a maximum, we see the differential of about 2 degrees at the mouth of Oyster Creek. If this were done for the full simulation period, that difference would be closer to 4. The next set of scenarios were the nitrogen reduction scenarios. And these are, as I said, these are done with the hydrodynamics with Oyster Creek offline. These also employed the marginal decrease in atmospheric deposition. However, all rates, constants, and kinetics are retained from the baseline. Inlets remained the same. Inlet forcings and loads remained the same, except for Point Pleasant Canal. We had to cap that at 450 micrograms per liter, or else the northern part of the bay would never be able to assimilate. Reductions are applied again to the entire watershed. So I want to reiterate, this includes all land uses. And this was done in an iterative fashion. At first, we applied uniform cuts across the watershed from 20 to 80% by 10% increments. And we needed to do this to constrain the magnitude of the needed reductions. Once that was done and a general number was arrived at, this was paired with the geographic targets. So we would run a 40, 60, 80% reduction in the north with 20% elsewhere. And this just shows, this is just a scenario summary by map. The left map is the baseline. The center map is the natural condition. And the map on the right is one of the first nitrogen reduction scenarios, where it's 60% in the north, 20% in the central and south. We see in the Central Bay, it's almost a natural condition, a bit higher in the lower, and we still have some disturbances up in the north. The Matiticon estuary still comes in at above 450 micrograms per liter. Now, once we substitute the 80 in the north, we see that the northern part of the bay really clears up, as does the north and the northern part of the central area. In fact, it actually gets a little bit lower than a natural condition. So it has a big effect. And this is the same data looking at it down the navigation channel. So just the model segments for the navigation channel were taken for this. And as you can see, the baseline, which is the black line, we see that nitrogen high in the north. The green is the natural condition. The red is the 40, the gray 60, the blue 80. What's interesting, we get down to the Barnegat Inlet, we see that they practically overlie. The effect of the inlet doesn't allow us to discriminate between the watershed reductions. And they're only slightly different when we get down into the south. Another interesting point is the dissolved oxygen graph in the middle. There really isn't much differentiation. We do see an excursion at the Point Pleasant Canal and at the Little Egg Inlet, and that's not so much due to the reduction in loads as it is a different forcing condition. And the bottom graph, just for informational purposes, is the chlorophyll A, and it pretty much mirrors what we see with the total nitrogen. We see the high in the baseline in the north, and they decrease appropriately with the decrease in nitrogen. And this is just a tabular way of looking at the scenario summaries according to assessment units. I believe Helen has showed this at the last meeting. So anything that's any values that are shown in red text, that denotes a mean concentration greater than 450 micrograms per liter. And this is why the state is looking at that 80-20 formulation to bring nitrogen down in the bay. So this is just a summary slide. We actually covered most of this. One point I wanted to make was, again, one other point I wanted to make again was that dissolved oxygen is relatively insensitive to both parametric changes and changes in external loading. Sensitivity analysis shows us that the most sensitive model variables are phytoplankton, chlorophyll A, and the inorganic nutrients, NOx, ammonium, and PO4, and they respond to parameters that are related to algal growth, such as the actual growth rate, respiration rates, algal stoichiometry, as well as mineralization parameters. And we'll end it there.
Hi, I just wanted to ask, you said under the natural conditions scenario, all watersheds were converted to the forest signal, but that doesn't discriminate between reducible and non-reducible land uses. What are reducible and non-reducible land uses? Like, can you give examples of each?
Well, so if you were running a watershed model, you would carve up a watershed by individual hydrologic response units. And each one of those response units would be a block of urban, a block of ag, a block of forested. So here, the way the model's loaded, it's loaded at the sampling point, at the outlet or the pour point of the watershed. So it's basically integrating all land uses within that watershed. So when we're taking that reduction, it's not just from developed land, it's from the watershed.
Okay, thank you.
Okay. In the chat, Christian asked, what percent of the DO balance at the navigation channel is SOD? It seems that carbon load reductions didn't change the SOD that much then.
We see, I don't know the exact number for dissolved oxygen, but what we see regarding SOD is the values are not as large as one might expect. I mean, there was some data collection done regarding SOD, and that study was biased towards shallow and carbon-rich areas. I ran some scenarios on the model looking to see how much SOD the model can assimilate. And what it looks like to me is that it can do something on the order of 0.4 grams per meter squared per day in the north and maybe 0.3 in the south. Anything beyond that, you will be driving dissolved oxygen into hypoxic conditions.
Thank you. No more questions in the chat.
Do folks have any additional questions for the department or anything that didn't get covered in these presentations? We have some time left, so we'd certainly be happy to field some additional questions or comments that you all have.
I couldn't make it here until just a few minutes ago, but I went online to the YouTube of the previous session. I couldn't find the question and answers. Were they on there?
We didn't have questions and answers from the last session. I mean, we did some verbal responses like this. It'll inform our writing of the TMDL document.
And were the questions after each session or each speaker, were they on the YouTube?
The questions were asked similar to how we're having today, and there would have been responses given and verbally, and that would have been part of the recording.
Thank you. And the comments were disabled. Why was that?
Well, I couldn't speak to that.
On the YouTube video?
Yes.
I'm not sure. I'm not sure.
I mean, the comments were the YouTube comments. Yeah. Would it be possible to have the comments on for the YouTube posting of this session?
We can certainly look into that, of course.
Thank you.
Okay.
Oh, we have.
It's very obvious that over the last however many years, there's been a lot of effort and time and money on this project. Based on that timeline I saw out in the hallway, has any work been done to capture kind of the total cost of this effort?
Interesting that you asked that. In our TMDL write-up, and that is our report that we issue that we will eventually submit for public comment and then to EPA for approval. We do have a TMDL implementation section. We will encapsulate the various funded projects over the years in that, because that speaks to what's already been ongoing to address the impairment. So we don't typically put dollar values with that, but we could certainly take that into consideration. For example, back in 2017, 2018, the department had put out a request for proposals for non-point source grant funding, and that RFP specifically put $10 million on the table. And so the department right there funded 13 or 14 projects throughout Barnegat Bay to do implementation. And that was at a cost of $10 million that we put forth. Obviously, the USGS work was a pretty penny. So, so yeah, I think that's something we could consider a tabulation of that.
Thank you.
Yeah, I attended a DEP, I don't know if they ran it or they were just part of the conversation regarding the Superfund site in Toms River. I'm sure Toms River residents are familiar with that. Anyway, my concern is that are you doing this in the interest of kind of cleaning up a mistake or setting an example for how we should approach our human living habits in the area, on the planet?
Right. I will answer that question
from goal, I guess,
from my perspective of the work that my particular office does. So we develop surface water quality standards. So for phosphorus, nitrogen, DO, fecal coliform, E. coli, so on and so forth. And then there's different designated uses: recreational designated use, aquatic life designated use, drinking water use for example. And so if the standard isn't being attained, then the water body is listed as impaired. We call that a 303D list of impaired waters. We submit that to EPA. And if we're not attaining the standard, and as you heard in the presentation today, we've created a site-specific standard for Barnegat Bay for nitrogen to tell us about the ecology if it's healthy. So my answer to your question is we're looking at this from the ecology of the most sensitive species that Helen had walked us through. And so that's why we have a nitrogen target, and we did the modeling work and what reductions we need to attain that standard. So that does not address Superfund sites and contamination from other sources. Our work is specifically related in this case to the healthy ecosystem as it relates to a nitrogen standard. There's obviously other programs in the department, site remediation programs, and other funding that address those type of impairments from those sources.
I guess my question is it sort of after something, we want to correct something that went wrong, and then do we want to prevent that from going wrong again? Kind of, I mean.
In the bay as it relates to the organisms, or are you talking more broad in context?
Sensitivity to how we can inadvertently impact these little tiny living things all the way up to something bigger.
Right, because they're the indicators of the health. I think that's where the work of the stakeholders in Barnegat Bay come into play, and that they look at all aspects of a healthy ecosystem, work with the locals and things of those line. But as far as what we could do everyday wise, addressing non-point source pollution in general, education related to that, all those activities from the larger scale then do work down to having a positive effect on that micro scale that we were talking about.
To bounce off that question, I realize that the next session is going to be implementation, but I want to try to help ask a question that I think might be on the minds of folks here. Is we're learning how we implement, how you came to the TMDL level. What does it mean to the community once a TMDL is established? Is this going to govern how municipalities are reacting to stormwater? Is this going to govern how the state reacts to stormwater? I think that's kind of where the questions are aiming.
Right. And you hit the nail on the head, and that is what we would talk about at that session. Okay. Maybe you want to speak a little bit, Grace, to the work that you're doing with education and outreach in general to the folks here.
So I work at Save Barnegat Bay. I'm the educator there, and the work that Save Barnegat Bay does primarily is to educate and advocate for Barnegat Bay. And through that work, we have been we've really focused on trying to empower the 37 municipalities that drain into Barnegat Bay and the leaders of those communities and how to manage their stormwater effectively and comply with the permits for DEP. And there's all kinds of nuance there. So the reason I'm asking that question is to, I think, highlight a little bit of what this woman was asking, and just kind of, if you could just touch on, just give us a little teaser, a little like elevator pitch of what the implementation will look like, the session will go over, so that we can understand kind of where this is all going.
Right. And I could speak to what we've done in previous TMDLs. We have done TMDLs in the northern part of the state, in the Passaic and the Raritan, that were on a larger scale like Barnegat Bay. In those cases, we had point source dischargers. So we're able to specifically put permit limits. But in the case of Barnegat Bay, with it being non-point source, the tools available to the department are the MS4 permits, the stormwater permits. Now, the new permit came out in the past, last year that had a lot more requirements in it. And so some of the additional ordinances and frequencies identified in that permit, the need to do WIP plans, watershed improvement plans are identified in that permit. We're going to pick up on that theme and have a little bit more detail in our TMDL implementation plan, but we would talk about that at the stakeholder implementation meeting. We will have the MS4 program come and talk about that. Under consideration may be what they call an additional measure. Is there something more related to nitrogen and a best management practice that could or should happen in the watershed that we would take into consideration? If we put that in the TMDL implementation plan, the future MS4 permit would then incorporate that into it. So that's the type of conversation we would have in greater detail at the next session.
Kim, thank you. You've mentioned that that implementation session is going to be in the spring. Is there sort of a tentative timetable on moving?
Just going to say spring.
What's the tentative timetable for the states moving forward with the establishment of the TMDL?
The TMDL. We would anticipate having a TMDL for 2025. I don't want to commit to sooner. I mean, there's a possibility sooner, but our commitment to EPA, Helen, remind me, it's 2025?
They only required audits of any will be complete by September of 2024. Will be paid by that. We did not specify much time.
Right. So we're in development.
Thank you.
Sure.
Hi, so I just wanted to ask if the average layperson wants to learn how to advocate for Barnegat Bay, where is like a good place to start?
Well, I'm going to turn to Grace and Stan to answer that question.
Come work with Save Barnegat Bay. Catch me afterwards.
Get involved and keep asking questions. Officials at all levels, local, state. Everybody has to be involved in protection today. See here, there's a tremendous amount of federal resources which have been brought in there. Those are important. State obviously is very involved, and we're all working to make certain that local government is also aware of it. Everyone's voice is very important.
Thank you.
I'm going to help answer your question. Do it at the local level, because I live, like I said, in Lacey Township, and I disagree with a lot of things that are going on there. And we get up at township committee meetings and we voice our opinion and we let people know the things that are going on and how important it is. And I think an important part of education is to let local governments know that their little piece of the bay is not just their little piece of the bay. It affects every single town, every single person that borders on Barnegat Bay. And there's a lot, in my opinion, I'm just giving you opinion, there are a lot more elected officials that need to know that that's the case, because they seem to be, some of them seem to be ignoring that. Anyway, thank you.
Okay, so we got one question in the chat from Charles. Most of the 80% reduction in the Northern Bay is likely to come from stormwater management improvements. How will this improved stormwater management be funded? Through stormwater utilities?
I think that's a conversation that we would have in the future.
Thank you.
Are there plans for future sampling events to monitor how the reductions are working? Is that something that the state has discussed on how you monitor if these plans are working out?
Yes, thank you. I appreciate that question. That's one of my favorite questions. Mostly because I'll answer the question in two parts. Back in the 1990s, the department did some foundational work of monitoring in the Toms River watershed. and then up north in the Whippany River watershed. And we will be revisiting those stations. So we have baseline data. And in the ensuing years, we've had stormwater regulations. We've had a statewide phosphorus fertilizer ordinance. We've had additional funding to do the best management practices projects that I talked about. And so we are revisiting those sites in the next several years, and we will do this comparison to the baseline data to what the data is showing us today. Of course, taking into consideration, of course, development has happened in the ensuing years. So we will be working with different programs in the department and applying the statistics to tease out what that information tells us. My hope, of course, is that we can show improvement, but I also feel if we've held our own and water quality hasn't gotten worse, but has stayed the same and development has continued, that to me is also a success. So that is one large project that we're doing. But for our TMDLs in general, an EPA requirement is that we do have a follow-up in our work to see if we're still continuing and we'll have a trend of improvement. So that's through the networks that the department already has in place for monitoring. Sometimes we'll do a special project, or other times we will just look to our network and then we'll add an additional site when they move stations around within an existing network. So therefore, we're able to determine that we're seeing improvement. It's a question in the back. Thank you for, yes. For those that didn't hear Helen's answer, and at the previous session, we had Bob Schuster, and he spoke to the long-term monitoring that has been going on in Barnegat Bay. And as Helen was just responding, we're in our third 5-year cycle of that long-term monitoring. So we're revisiting the same stations. Bob presented data that did show that there's already been some improvement related to that data. So all that we tie in together and put that into our TMDL implementation plan.
And by the way, thanks for great presentations today. And this is obviously super complicated work that's been going on for so long with the department and all the stakeholders, Barnegat Bay Partnership. But I'm just curious to know if the dots are being connected between the coastal resiliency and habitat work that's happening in and around the bay, and the work that's planned to take a look at what are the impacts from to what we're all concerned about here with the TMDL, nitrogen, phosphorus, TSS, so that when this TMDL gets put into place finally, we'll understand which projects are going to work best to address nitrogen, phosphorus, total suspended solids, if that's going to be a TMDL at some point. In other words, is anybody at DEP connecting the dots between all of this effort that's going on for restoration, coastal resilience, with this whole issue of the the contaminants in the bay?
Stan, did you have some thoughts on that? You were sort of nodding your head, I think, in agreement.
I mean, this TMDL is going to be a driver for a lot of projects once it gets put into place.
There are more justifications for backing of the behavior. Hard shorelines, there's more waving, more sedimentation out of sediment in the day. That's a continuing issue. Sea level rising. So those shorelines, RAP sediments, processing, lots of good logical support options that help us use it.
Yeah, I mean, we
have a hard time not wanting to be in the water trend.
right.
So I think land use has to be an increasing component of everyone's focus.
And probably all of us here know that, right? Essentially, I mean, it's almost commonsensical, but are we looking at the actual, is there a way to look at the impacts now so, that are the benefits or maybe not benefits of some of these coastal resilience projects to this issue, so that when the TMDL gets in place, we can hit the road running. What's going to work, what's not going to work, what's going to be the most beneficial, what's not going to be the most beneficial.
We is working with a lot of groups together on
Yeah.
that. It takes a lot of resources and it takes a lot of.
I know our thoughts are going to be, but I think you know, it's really work.
Yeah. I mean, because all of these projects that are being put into place in Barnegat Bay that you all are, gratefully doing, are unique opportunities to learn what's going to work and what's not going to work for this particular issue.
I don't disagree with all, and you said, everyone here in this room is aware of these issues. Solution involved now, the investment, a lot of them.
Yeah. Maybe we could put some effort into that. But when there's funding available for coastal resilience, maybe you can build into the monitoring of those coastal resilience projects or habitat projects, some sort of, let's look at what's happening with nitrogen, let's go phosphorus, let's learn from that so that, like I said, hit the ground running when the time comes. That's all.
There have been a couple of proposed federal projects too, to look at some big picture landscape things. About right now, good reason to talk.
Okay. So thank you, everybody. We appreciate comments and concerns that were raised today. We anticipate, as I said, later this spring, having our final session, and that will be about TMDL implementation. What does that mean when we put forth the TMDL? What does that mean at the local level? We said today's session has been recorded. We will look into that comments on off feature to address the concerns that were raised. The presentations will also be posted. The department had posted to our event notice calendar. So everybody that has registered and is in attendance today, there will be a follow-up email in a week or so's time where you can find today's recording and the presentations. So if you have any questions or thoughts or follow-up, if you'd like to have a follow-up meeting with the department and share your ideas, we're available to that. And I'll point out also that the first session was posted to the event notice calendars and the presentations are there as well. We appreciate everybody's being with us as we, I think, delivered on our promise to delve into the science. I think you would all agree. We got a lot of good science, a lot of details. We wanted to take the time so that you all understood what goes into developing a TMDL. This is not an Excel spreadsheet desktop type model. This is the real deal. And it takes time, effort, money, but many people have spent blood, sweat, and tears on this. And I'm grateful to help see it through to fruition. And thank you for all being part of that with us today.